Hello friends, welcome back to another lesson today. Last we left off, we learned about Newton's laws of motion, and in this video we're going to be building on that and look at a common misconception associated with the third law. So let's revisit the third law real quick, which states that if object A exerts a force on object B, then object B also exerts an equal and opposite force on object A. And I think a lot of the time people get confused by this statement because they think that if they actually apply this law, that no movement should be occurring. And let me explain that a bit further. Say I have a ball, and I throw this ball with some force towards a wall. So let me draw in a wall here. So upon contact, I'd expect this ball to exert some force on this wall. So I'd say F B on the wall, and we'd expect the ball to also experience some force, which will be equal and opposite, and so we'll call that FWB for force of the wall on the ball. So you might say that these forces cancel out each other, so nothing should really be moving in this diagram. Because our understanding of Newton's third law says that each force has an equal and opposite reaction force. And you'd be right if those forces were acting on the same body. However, there's a crucial detail that we're overlooking here, and that is the fact that the forces are actually acting on different bodies. The ball is exerting a force upon the wall, and the wall is exerting a force upon the ball. And if we consider Newton's second law, which says that an unbalanced force produces an acceleration in a body, what we're concerned with are only the forces acting on the object itself. So if we look at the wall itself, the only force that it's actually experiencing is the force of the ball making contact with the wall. So that's this force here. And this force here, FBW, is the one causing acceleration in the wall. Now it's true that this wall will also produce a force, but that force will not act on the wall. It will be acting on the ball. So the ball, which was red, so let's draw that ball as red, will be experiencing a force from the wall, and that will be FWB. And both of these unbalanced forces in both of these scenarios will cause the acceleration in the object itself. And if we take into consideration Newton's second law, which is just F equals ma, we see the mass of the wall is so much greater than the mass of the ball that the acceleration produced in the ball will be far, far greater than what's produced in the wall itself. So I think a better way to describe Newton's third law is that forces always occur in pairs and are of similar nature, and the forces are of the same magnitude, but they act on different bodies in opposite directions. Now let's consider a ball resting on the ground. So let's say we have some ball that's resting on the ground. So that's my ball, this is my ground. And let's look at all the forces that are acting on this ball. We know the ball is going to have some weight force caused by gravity, so I'll draw that in as W as my weight force. And as a result of the contact between the ground and the ball, there will be a normal force which will push up on the ball itself. And I will label that as the normal force, so N. Now a normal force is the result of a contact between two objects, and it always acts perpendicular to the surface. So I'll write those two notes down. Perpendicular to the surface, and it's always a result of the contact between two objects. So if we take a look at the normal force and the weight force, are they consistent with the definition of the third law? Well, as it turns out, they're not. If we go back to our definition of the third law, we notice a couple of things. The normal force acts on the ball as a result of the ground pushing back on the ball. But the weight force is also acting on the ball due to Earth's gravitational field. So that's our first violation, because we have two forces acting on the same body, which in our case is the ball. We've got the normal force acting on the ball as a result of the ground, And we got the weight force acting on the ball as well because of gravity. If I was to take away the ground from this diagram, that normal force would no longer be there because there would be no contact between the ball and the ground. So the only forces remaining on the ball would be the weight force imposed by Earth's gravitational field, which would be our weight force. So it's quite easy to see from our definition of Newton's third law that these forces don't occur in pairs, and even though they might be of similar magnitude in this case, they act on the same body, which is the ball. So let's consider another scenario over here. Let's say we have the same ball resting on the same ground, but now I place my foot on it so that I'm applying a force downwards like this. So I've got my foot force. Let's call that F of F. I know the ball's still going to have some weight force associated with it, caused by the gravitational pull, so I'll call that W. And I know that there's also going to be a normal force due to the contact of the ball with the ground. So let's go ahead and draw that in as well. So we'll call that N. Now I know this ball over here isn't accelerating in the Y or the X direction. So what can I say about the force balances here? And let's label that as N. I can say there's two forces acting downwards, which are F of F and my weight force. And I know this normal force has to counteract this because there's no acceleration occurring in the Y direction. So my normal force will be equal to the force of my foot plus the weight force. So it's pretty clear to see that the normal force here doesn't always equal the weight force. So they're not exactly force pairs here either. So then the question becomes, where does this normal force actually come from? And if N is not the force pair of the weight force, then what is? Well, if we go back to the example of our ground being taken away, which was over here, what we're left with is the ball itself, and there's no ground, and all we have is the Earth, or the Earth's surface. So we have gravitational attraction between both of these objects that they impose on each other. And because the Earth's mass is so much greater than the ball's mass, the gravitational acceleration felt on the Earth will be tiny in comparison to the gravitational acceleration felt by the ball. And the force pairs would become the force of gravity imposed by the Earth onto the ball, and that'll be FGE. And the force that's felt by the Earth will be the force of gravity imposed by the ball, which we'll call F gravity caused by the ball. And FGE and FGB will be equal and opposite to each other, and that'll be the force pairs. And what about our normal force N? What is the force pair for this force? Well, if we consider the diagram, the normal force occurs due to the contact between two bodies. The ball will be in contact with the ground, and it will push down on the ground this way, and the ground will push back on the ball, which will be known as the normal force. So our force pairs will be the normal force, which is caused by the ground pushing on the ball, and the force pair to that will be the ball pushing down on the ground. Now let's consider one more scenario before we wrap up this class. Let's say I have a sloped ground. So let's say we've got a sloped ground like this. And let's say there's a ball, or let's say there's a block on this sloped ground. What would the forces be acting on this box over here? And let's give this sloped ground some angle, so we'll just call that theta. And let's look at all the forces. So we know there's going to be a weight force acting straight down from the center of mass towards the center of Earth, so we'll say W. We know there's going to be a normal force as well because there's contact between this box and the ground. So we'll draw a normal force acting perpendicular. Can we say in this scenario that N is equal to W? Well, let's find out. Well, we know forces are vectors, so we can break them up into their components. So I can break up my weight force so that it's in the direction of W. So my weight force becomes these two components. And my normal force also has two components, where one will be in the y direction and one component will be in the x direction. So that'll be nx and that'll be ny. And just by this diagram alone, we can go ahead and say that ny has to be equal to our weight force because there's no acceleration occurring in the y direction. So once again, our normal force will not be equal to the weight force. So these two forces, the weight force and the normal force, are not force pairs and are something that shouldn't be confused whenever you're looking to analyze a problem. However, this is quite a common scenario that you'll come across in physics questions, and it's important to know how to allocate angles such that you're able to break up these weight forces and these normal forces effectively. So let's have a quick look at that before we close out this lesson. So let me get rid of some of the stuff on the screen here, and let's go ahead and extend our lines. So if we're looking at the weight force, let's extend this weight force over here right down to the base of this slope that we've drawn. So if I got my green weight force, let's go ahead and extend that all the way down to the base. And I'll draw in the base as well in black. And let's go ahead and extend this component as well. And let's do the same for the normal force. So let me get rid of all this. And let's extend out those lines. So we got that going up, and we have this going up. And since we're looking at this box as a single point, I can bring this interaction of forces right down to the ground over here, so to the surface. And let me redraw those lines to match that. So our lines then become this green line over here, and from here we have another component of that weight force, which I will also draw as a line like so. And from there we can also draw our normal force, which is going to be up here and up here. Cool. So what if I want to find the angle over here and I want to find the angle over here such that I'm able to break up the normal force and my weight force? Well, let's start by filling in all the angles we already know. We know that this is going to be a right angle triangle. So is this. We know that this here is also going to be a right angle, and that's because we can resolve a bit of the weight force into its perpendicular component with the with the surface. We know that the sum of all the angles in a triangle are equal to 180. So if we look at triangle 1 over here, we have theta plus 90 plus, we'll call this alpha, this angle here, gamma, and that'll be equal to 180. And if we do a little bit of arithmetic, we can say that gamma is equal to 180 minus 90 minus theta. And if I look at this angle here, which is alpha, I know that alpha plus gamma is equal to 90, so I can say alpha plus gamma is equal to 90. And I can plug that back into the equation over here. So I can say gamma is equal to 90 minus alpha. So 90 minus alpha is equal to 180 minus 90 minus theta. And if we do a bit of arithmetic there, we get alpha is equal to theta. So this angle here, alpha, is going to be equal to theta. And what I might do is just have a side diagram here, a mini diagram rather, which will show all the forces that are acting on this box. So just so that you don't get confused. So we've got the normal force, which is perpendicular. we've got the weight force acting straight down, and then we can divide these into our components, and I can do the same thing for the normal force, so that can be in that direction. And that's essentially what I've drawn in this bigger diagram, but I've just extended all these components out, and we're looking to find the angles over here and over here. So let me label that as N for normal. Now we notice that this normal force will have a corresponding component of the weight force acting in the same direction, so that'll be one line. And then we'll have the actual weight force, which will be in the y component, in the same direction as the y component of normal force. So we'll have two lines that are vertically opposite. And if we go back to our geometry properties from high school, we'll notice that there's two vertically opposite lines here which form the same angle in between, such that this angle here, which we called alpha before, will be the exact same as that angle, which we'll call as beta. So alpha will be equal to beta, which will also be equal to theta, which we proved below down here. So whenever you're looking at problems on an inclined plane, you can go ahead and break up the normal force and the weight force into its constituents or its components, and you can say the normal force, which will be pointing perpendicular to the surface, will form an angle of theta, where theta is the same angle as the angle that the slope forms with the ground. And similarly, when we have our weight force, which will be pointing downwards, the components of those weight force will form the same angle theta up here. So that brings us to the close of this lesson. I hope it helped you clarify any misunderstandings that you had about Newton's third law. And we also took a brief look at breaking up the forces into their components. So I hope that both of these things are solidified, and we'll obviously get to practice these on the coming lessons and coming questions. So I'll catch you at the next one. Thanks for your attention, and I'll see you soon.